Hi guys, I'm Shriya and today's video will be on topic 11.4 phase changes. So let's start basic and look at some phase changes. Remember that delta H is enthalpy, or the change in heat energy as a process takes place. And looking at this chart here, going from solid to liquid, the phase change that we have here is obviously melting. And the way the enthalpy change is measured for the process of melting is actually counterintuitively known as heat of fusion. And the enthalpy for the opposite process, freezing, is the negative heat of fusion. So try not to get this confused. Then we have the enthalpy of vaporization, which is the heat needed to convert liquid into gas, and for the reverse process, condensation, in the same way we did before, we just put a negative before the heat of vaporization value. Finally, we can look at the change straight from solid to gas, which is sublimation. And think about how we can measure the heat of sublimation. So you might have guessed that we add the heat of fusion and heat of vaporization for the substance being examined. And the same can be applied to the opposite process of sublimation, which is deposition, and we can find the heat of sublimation and take the opposite value, or which is the equivalent of adding the negative heat of fusion that corresponds with freezing, and the negative heat of vaporization, which corresponds with condensation. And we can see that the overall, as the system gets more disordered, going from solid to liquid to gas, the energy of the molecules in the system increases. So here we have something called a heating curve, which basically puts together the phase changes and corresponding enthalpies we just talked about against an additional factor of temperature. So we know that overall average kinetic energy, temperature, increases when we add heat to a substance. The molecules get farther apart, resulting in a transition to less dense states. And what can be confusing about this is that because temperature is defined as average kinetic energy, sometimes we think of an increase in particle motion being the result of increasing temperature, when it's really the other way around. So looking at the change into a gas state here, for example, we have to remember that temperature is on the y-axis, so the molecules aren't getting more disordered because the temperature is increasing, but the average kinetic energy of the molecules is increasing because it's changing into a less dense state. And the reason it's changing into a less dense state, you might be thinking, is because of heat. So that's where heat comes in, which is on the x-axis. And remember that heat is different from temperature. If you remember back to specific heat, the specific heat of a substance is the amount of heat energy it takes to raise the temperature of a substance by a degree Celsius. That means the lesser the slope of a line, the more heat, across the x-axis, that we need to increase the temperature, and therefore the higher the specific heat. So we can see here that the specific heat of ice is lower than the specific heat of liquid water because the line is steeper. The next thing you probably notice is the areas where the temperature seems to stabilize at these horizontal lines. Here, the reason that the temperature isn't changing is that because what's happening is basically any heat being added in these stretches is going purely towards a phase change. So basically when adding heat, if you look at the heating curve, the only time that the heat affects or increases the temperature is when it's increasing the average kinetic energy of the molecules in a single phase. So when heat is being involved in a phase change, the net particle motion isn't changing because the system is in equilibrium between two phases, if that makes sense. So here in this stretch, the heat that's being added isn't actually melting the ice until it reaches the start of this horizontal line. By the end of this horizontal line, that's when it's completely changed phases into liquid, and then any heat added from this point onwards is once again only affecting particle motion only, but it's not actually starting to boil the water until it reaches, of course, the boiling point and then the phase change is occurring here. So finally we have this concept called critical temperature and critical pressure. So how the book starts by describing this idea is that so basically we have a given amount of vapor, generally, if we have a given amount of vapor, if we apply pressure by, for example, if you look at this piston model here, if we increase the pressure of the container by lowering the piston, at some point the vapor molecules are going to sort of condense into liquid. And this is the liquefaction process for a gas. So here in this example, if we have liquid water, for example, at 100 degrees Celsius, the amount of pressure that we need to start the liquefaction, or how much this piston needs to be compressed here, is 760 torrs for it to start liquefying. At 110 degrees, we need 1075 torr, and finally at 374 degrees, we need 1.655 times 10 to the 5th torr. So we can see an obvious trend here, that as the temperature of the liquid increases, the more pressure, of the gas increases, the more pressure we need for the liquefaction process to begin. Now note that at 374 degrees, for example, we're so high above water's boiling point that normally if this was an open container, we would have obviously completely evaporated the liquid. But if we apply this huge amount of pressure, we can see, as we can see by this huge value in the scientific notation, we can manage to produce just a little bit of liquid, because remember, this is the pressure that liquefaction starts occurring. So then you might ask, can we just keep going and adding more pressure with more temperature? But if you think about this, logically, if the temperature is 1,000 degrees, no matter how much pressure we have, logically there isn't going to be any reverse process to vaporization, and confining so much probably isn't even possible. So there is a temperature and corresponding pressure for every liquid that is the highest temperature and pressure that it can exist at, or in corresponding pressure. So here with water, the 374 degrees, and at this pressure, this 217.7 atm, is this limit. And these are graphs that you're going to see related to critical temperature and pressure, and they're pretty self-explanatory, and just understand that they're different for different substances. Okay.